So, looks like we're kind of light on people today, but that's all right. We'll live. We'll be fine. Did you guys want to take a few more minutes to look over those group assignments, or just kind of start with the next stuff? So I promised yesterday I'd give you a little more time with the group assignments, but I guess I'll leave it up to you at this stage. Did you guys get a chance to finish those yesterday, or so you want to continue working on those for another 10, 15 minutes, or just kind of move on?
I finished mine.
You finished yours? Okay. How about the rest of you?
I finished the first one and halfway through the second one, but then I kind of got stuck on the second one.
Okay. So why don't we talk about it a little bit more, and then then I can either give me more time or we just kind of move on. So let's see here. Good. So where did you get stuck on the second one?
The part B with like finding the acceleration.
Oh, okay. So good. So basically I told you the density and I told you the volume, right? Because it's basically a disk which has a thickness to it. So in this case, the volume then would be the area of the disk. So that's just the area of the circle. So it's going to be pi r squared times the thickness. So that's going to be the volume. So let's write all that out. Yeah. Good. So in this case, we know that the mass then is going to be equal to the density times the volume. So it's going to be equal to the mass density times pi r squared times the thickness, right? So this is just the volume term. And then what you know is that the sum of the forces, so Newton's second law says that the sum of the forces must be equal to the mass times the acceleration. So in this case, the only force acting on it is the radiation force. So this is going to be equal to the mass, which is the density times pi r squared times the thickness times the acceleration. So that means the acceleration then is just going to be that radiative force divided by rho pi r squared times the thickness. So here you're told the diameter. So the diameter was 9 meters. So you almost have to say the radius then is going to be 4.5 meters. Good. So this is what's going to give you then your area, or it's not area, sorry, acceleration. So it's going to be part B. Good. So then part C again is just saying, okay, so if I look at the size of that acceleration, is this going to be large enough for things like space flight? So meaning if I wanted to travel from, say, Earth to Mars using the radiation from the solar sail, or using a solar sail, so the radiation from the sun, is that something that's going to be feasible? The answer is going to be no, because once you actually multiply all these numbers out, you should find that this acceleration is ridiculously small. So in that case, then, you can't use it for large travel, but you could use it for things like, small, fine adjustments. So for example, if you were trying to work on, so if you're using the solar sail to work on like the Hubble Space Telescope, for example, so you could use it to move around to do fine adjustments as you're moving that thing around, but you couldn't actually do large space travel with that. Right, and then the last part is more just kind of conceptual thing. So how could you actually make this accelerate faster? So basically from here, we can see is that the acceleration is going to be the same thing as f rad divided by the mass times the acceleration, or sorry, is equal to the acceleration. So this is fixed. This is a fixed number, which means that this thing, to make this as big as possible, we want to make this as small as possible. So basically part D is then asking, how can I make the mass as small as possible? So let's go back to what we know. So what we know is that the mass is equal to the density times the volume, right? So if I want to make this as small as possible, there are two things I can play with. I can either play with the material, so I can decrease the size of the density. So we could use a less dense material, for example. Or I have to play with the volume. So we have to then minimize the volume. But the problem with minimizing the volume is, remember that the radiative force is equal to what? The intensity divided by the speed of light times the area, right? So basically, if I want to make the radiative force as big as possible, the intensity is fixed, the speed of light is fixed, so I want to increase the area. So to make this guy bigger, we have to increase the area, which means that to minimize the volume, if we want the force to be as big as possible, then we want to not really minimize the volume, because the only thing we want to minimize the volume in would be with the thickness. So I want to make it basically as thin as possible to make the volume as small as possible. So the best thing to play with, the gist of all that, is to play with then the material. So the way to get it to accelerate the greatest would be to use a less dense material then. Right? Because this said that we were using a material that was, where is it? There it is. 1,700 grams per centimeter cubed. So basically we would have to use something which is less dense than this, basically. Okay. And that's all the second one. Sound good. Sound good. Everybody else okay? Not too bad. Good. All right. So good. How'd it go with the third one? Okay with the third one. So that one I gave you a number to work for, so it's not too bad. Good. All right, so let's get rid of these and let's go ahead and start on new stuff. That sounds good. So good. So today we're going to start the last chapter, which is in chapter 23. Probably the last chapter. I don't know. Depends on how much we get through in the next couple of days. We might do some more of that. But basically, chapter 23 wants us to start thinking about light again, right? So basically, when we think about an object that we want to start looking at, we typically are going to think about light, and there are two possible ways we can see an object. Because remember, the point of light is light gives us the most amount of information. So basically, almost all information we use, information which is available to us, is in the form of light. So pretty much almost all information that we use comes in some form of light. So light is our greatest amount of information that we can use to do experiments with and to gain information about an object and etc. So having said that, basically there are two types of way that we get this information. So types of ways to gain information. The first way is when the object itself generates light. So the object generates light. So for example, you see a light bulb, you see a star, you see a planet, well, not a planet, but you see a star, you see a candle, you see things like that because the object actually generates its own light. So this would be from like a candle, a star, light bulb, flashlight, all of these different things. So the object itself is actually what's generating the light. The second way we usually see things is when the object actually reflects light. So this would basically be other things. So for example, we see planets this way. We see each other. We see, for example, my desk, cars, when they don't have their headlights on, etc. So most of the things that we actually see are when the object itself reflects light. So in that case, the light bounces off the object, and then we can see it using that reflected light. So for this remaining portion of the class, we're going to be mostly looking at things like this, things that are actually reflecting. So for us, we will primarily focus on reflected light. Most of the reason for that is because at this stage, we don't understand how an object actually creates its own light. That wasn't fully understood until after the time period that we're talking about all this stuff, so closer to the 1930s. So how it actually generates light is actually via quantum mechanics. But since we're actually not going to talk about quantum mechanics, then we're going to kind of skip that part. So pretty much anything that we're going to talk about, we're going to assume that it's going to be reflecting that light. Okay. And then we're going to look at how this object actually works when it's reflecting light. Now, of course, we could be looking at something which is like a candle, something that's generating lights. It's not going to change really anything that we're going to talk about, but again, we're just going to kind of focus more on the fact that it's more reflecting light. So that's how it's actually generating light. So we're not going to worry too much about how it actually generates light. So the first thing we're going to start talking about is what's known as the ray model. So what is the ray model of light? So ray model of light is, say I have some sort of object, and either this thing is creating its own light under the first version, or it is just reflecting light. The way it's doing this doesn't really matter. But what's basically happening is when something reflects light or creates light, near the object itself, it actually creates what are known as spherical waves. So these are waves which propagate out away from the object in spheres. So even though I'm drawing circles here, this is actually a three-dimensional object. So each one of these lines or circles that I'm drawing, this then is going to represent a wave crest. So this is a wave crest moving away from the object. At the speed of light. Which basically means that's what? This thing is moving outward in these directions, all at the speed of light. And these are all moving at c. So basically when I'm drawing these, think about it's a wave crest, so much like a water wave that's moving, and this is just the crest part, so the highest part of the wave, which is moving away from the source, again, at the speed of light. Now, as we talked about yesterday, what happens is what? Even though near the object, this thing starts off as spherical waves, but as the waves get further and further and further away, these things are going to start to create flat lines, which is what we call a plane wave. So this is a plane wave. So again, this sphere, imagine the sphere is getting bigger and bigger and bigger and bigger, and eventually what's going to happen is that sphere becomes so large that each one of these sides of the sphere, even though it's technically spherical, appears to be something which is flat, right? So think about the Earth, right? So the Earth is actually close to a sphere, but to us in a local area, when I look at my house or if I look at something around me, it appears to be flat, not something which is actually spherical. So it's just because the radius has become so much bigger. So as I mentioned yesterday, this is what's known as the far field limit. And this is where we're going to look at most of our rays here. So this thing is still moving. So each one of these rays is still, or each one of these wave crests are still moving outward at the speed of light. But again, it's just that we're so kind of far away that the radius has become so large that they appear to be straight plane waves. So the ray model then is going to be, we're going to draw a line which is perpendicular to the wave crest, which is then pointing in the direction of wave travel. So this is going to be a ray. Okay. So anywhere along here, we're just going to draw a line which is then perpendicular to this sphere. And again, each one of these is going to represent the direction at which this thing is traveling. And each one of these we're going to call a ray. Okay. So the nice thing about the rays then is it's basically just a line instead of drawing these wave crests, which represent the direction at which this wave is moving. So that means here, all these velocity vectors effectively are going to become a ray. So basically each one of these is going to be a ray, which again is showing the direction at which the wave is traveling. So the wave crest. This is one way to draw it without drawing these wave crests. So what that means is by the time it gets out here to this far field region where these guys are being plane waves, that represents on here a very small area here. So these plane waves that are here started off in a really tiny area from this sphere and now have blown up to create this ray diagram here. So this ray diagram that we're looking at here, so these plane waves came from this very small section here. So these are very small section of the original spherical wave. So again, a ray, or the ray model, is basically just a way to represent these wave crests, the actual wave, which is moving away from the object. Again, whether this is due to the fact that it's reflecting or if it's actually creating its own light, at this stage it doesn't matter. But again, all the rays do is they represent that they are perpendicular to the wave crest, which are moving, and they're pointing in the direction at which the wave is traveling. So if you want, you can just think about them as velocity vectors, which are perpendicular to the actual object themselves. So we're going to be interested in primarily when the wave interacts with a boundary. So here's our boundary. And again, we know that this is electromagnetic radiation, which means it's a wave, and this thing is going to interact with a boundary. So if we go back to what we talked about way back when, remember that when this thing interacts with a boundary, one of two things are going to happen. So either the initial ray, which is coming in, so here's my initial ray. You can draw that a little bit better. There we go. Let's draw it in the opposite direction. So my initial ray, which is coming in, say this ray, this is coming in at an angle theta 1, where theta 1 is equal to the incident angle relative to the normal line. So this dashed black line here is what we call the normal line. So this is called the normal line. And this is at 90 degrees perpendicular to the boundary itself. Okay. So one thing that's going to happen is that this ray can be reflected. So this is going to be our reflected portion. So this is the reflected wave. So this is going to come off at an angle of theta reflected. So let's call that theta r. And then the other part is the refracted portion, where that refracted portion is going to come down in this direction. So this is what we call the refracted or transmitted portion. Refracted / transmitted. So basically, what we're going to be looking at for the first part, actually throughout this entire chapter, is how an image is created. So basically, how do we see an image based off of both reflection and transmission? So how do we actually see an image? So let's say here, I have an actual object. So here's my object, which is creating that wave. That wave then is coming in, striking this boundary, reflecting off, and we're going to be looking at first is my eye is going to be here, and I'm going to look at the image formation due to this reflection. Okay, so this is the first step we want to focus on. So first, let's look at reflection. So let's concentrate on that one. So in reflection, the object starts off in one medium. So this is medium 1, and stays within medium 1. So it gets reflected back into medium 1. As opposed to in refraction or in transmission, it's going to end up in a second medium. We'll talk about how to deal with that in a little bit. So reflection. So how does reflection work? I don't know where that black line is. That's fine. So let's get rid of you. There we go. Good. So first thing is we need to talk about what's known as the law of reflections. So what the law of reflections basically says is, and this is based off of empirical law. So this is empirical law, where empirical basically just means that this is based off of measurements. What it says is that the angle of incidence, so the angle that this object or the ray is originally coming in relative to the normal line, is exactly equal to the angle of reflection, where the angle of reflection is the angle that it reflects off at relative to this normal line. So this is what's called the law of reflections. So law of reflection says that this ray, which is coming in, bounces off and then goes out. This angle here is exactly equal to this angle here. Now, this is true on any type of surface. So here what I'm assuming is that this is a flat, smooth surface, but even if it wasn't flat and even if it wasn't smooth, this would still be the same. So for example, if I had a curved reflecting surface, which we're going to look at in a little bit. So here, if I send in a ray, where that ray comes in and hits the surface and reflects off, so here I would draw an instantaneous normal line. So that would be this normal line here. I have to be that in black, that's fine. So here's my normal line. So this angle here, theta of incidence, would still be equal to the angle of reflection. So this would be my reflected, and this angle here would still be the same as that other angle. Okay, so regardless if this is a curved surface or not, this law of reflections is still true. And the reason for that is, as I kind of mentioned earlier, if you think about the Earth, this local section around this point where this thing is actually reflecting off of is still flat. This is a flat section. So if I make this area small enough here, this still represents a flat section. So the law of reflection says that this angle here has to be the same as this angle. So this is what we call the law of reflections. So good, so let's use this and let's do an example. So this example says that we have two flat mirrors which are perpendicular to each other. An incoming beam of light makes an angle of 15 degrees with the first mirror. So that's this angle down here. So this is 15 degrees. And it wants to know what is then the angle, this angle here, at which it comes off of from the second mirror. Okay, so this is our first thing we want to look at. So good. So let's redraw our picture. So here we have, here is my two perpendicular mirrors. So here's the first mirror. Perpendicular to that is the second mirror. So here's my second mirror. We know these two guys are perpendicular and these are reflective surfaces. Okay, so then we're told that what? We have an incoming incident ray. So it's this one, comes in and strikes here. Okay, where we're told that this is the incidence angle, theta 1, which is then equal to 15 degrees. Okay. So after it strikes, what will happen then is this guy's going to get reflected. So this guy's going to bounce off here. And then it's going to hit this mirror. So that if this is a perpendicular here, then this is also perpendicular here. And then this one is going to also be reflected. And then finally, this one's going to reflect off in this direction. So again, what we finally want to know is what is this angle here? So let's call that theta, I don't know, theta final. Okay. So ultimately we want to know what is theta final. So good. So first things first, if I know this is 15 degrees, and I also know this is what? 75 degrees, because this has to be a 90 degree, which means this plus this has to be equal to 90 degrees. Now the law of reflection says that, well, if this is 75 degrees, which is the initial incoming light, then the reflected light also has to be coming off at 75 degrees. Right? So this is based off the law of reflections. So the law of reflection says that this angle here, so let's call this equal to theta 2. Theta 2 then has to be the same as, pardon me, this angle here. Okay. Now, since this is perpendicular here, then now we also know is that this is also 75 degrees. So let's call that theta 3. So theta 3 here is also the same thing as 75 degrees based off of what we know from high school geometry, that alternate internal angles have to be the same. So since that then is what? 75 degrees, that means that this little angle here, so let's call this angle inside of here, theta 4. Theta 4 then has to be equal to 15 degrees because again, this angle here has to be 90 degrees. So 75 plus 15 again equals 90 degrees. So the law of reflections then says, well, this angle here then has to be the same as theta 4. So this also has to be theta 4, which means that this also has to be 15 degrees. And then finally, since this all has to be equal to 90 degrees, that means our final angle then must be equal to 75 degrees. So theta final then must be equal to 75 degrees. Okay. So not too bad. All based off of the law of reflections. So good. So what about then the image formation? So what can we talk about, or what can say about the location and the height at which the object is going to be formed? So to do that, let's say that here I have my source. So this is my source. So in this case, it's a candle creating its own light. Here's a plane mirror, and we want to know if I was looking into the mirror, where exactly would this formation be? So where would I then see this type of image? So where would the image be created? So basically, to do that, we're going to draw a couple of representative lines. So a couple of different rays. So the first ray we can see is going to be this one. This one's going to come in, strike the mirror, and then bounce off according to the law of reflections, which says then that this angle here relative to the normal has to be the same as this angle here relative to the normal. This ray we're going to draw, this one's going to be slightly down further. This one's going to bounce off, which means the reflected ray will be below the initial ray. But again, this angle here has to be the same as this angle here due to the law of reflections. Now your eye, so let's talk about your eye. Your eye is actually pretty stupid. Kind of an abrupt way of saying it, but it's kind of stupid. Your eye does what's called ray tracing. So your eye is going to follow each ray that comes into your eye, and it's going to follow it in a straight line such that it's going to think the ray came from a place that it did not come from. So this is called ray tracing. So this ray, which came into my eye is going to follow that backward, and it's going to think that the ray actually came from this place on top of the image. And then this ray, even though it got bounced off and reflected, my eye is going to follow it back to a place at which it thinks it originated from, which is this location here. Okay? So our eyes do what's called ray tracing. So our eye sees a light ray come into us, and we think it always moved in a straight line. So we're going to follow that back along the line at which we think it came from to the location at which it seems to appear to have originated. That's why this thing is called the apparent source. So this is actually the image. So our eye thinks that this ray here started at this location. This ray started at this location. So it's going to follow it back to the location at which it thinks it originated from, which is then the image. Okay. Now, if we did some geometry on this, what we can see then is that this triangle here is exactly the same as this triangle here, because this angle here is the same as this angle here, which basically means that the distance from the mirror of the source is exactly the same as the distance from the mirror to the image. Meanwhile, the height then of the source is going to be exactly the same as the height of the image, because again, this triangle here is exactly the same as this triangle here. So when it comes to plane mirrors, what happens then is if this is my plane mirror, and this is my source, so this is my source, or what we just simply call the object, then the image which is created, so where this is going to be my image, or the apparent source, so this is what's known as the apparent source, or for short, the image. For plane mirrors, what happens then is that this distance from the object to the mirror, which we're going to call the object, and this distance here from the mirror to the image, let's call that the image, are exactly the same. So for a plane mirror, what happens is that the object location is equal to negative of the image location. And the height of the object is then equal to the height of the image. So this height here is what's known as the image height, and this height here is what's known as the object height. Okay. So for a plane mirror, it turns out that the distance that you see the image created behind the mirror is exactly the same as the distance you are away from the mirror. So basically what that means is when you're standing in front of the mirror, I don't know, brushing your teeth in the morning, then the image that which you see yourself in the mirror is exactly the same distance away from the mirror than you are to the mirror. So for example, if you're standing 1 meter in front of your mirror, then your image is 1 meter behind the mirror, which means you're a total distance of 2 meters away from each other. The height is exactly the same. So if you see your head in that mirror to be, I don't know, half a meter, then your head is still a half a meter in the image. Okay, so those two things are the same. So let's talk a little bit about this image. So this image is what's called a virtual image. And it's called upright. So this is an upright virtual image. So what's a virtual image? So a virtual image is an image that no light actually passes through that image. So this has no light actually passing through it. Okay, so what does that mean? Well, that means if I took this pad of paper, for example, and I was looking at my image in the mirror, if I put my arm behind the mirror and I put the piece of paper there, no light would actually make it to where the image is behind the mirror. So all the light in this case would simply come in, strike the mirror, and bounce away, which means that there's no light that ever goes through here. So no light rays are actually passing through this image. So this is what we define to be virtual. So virtual image means that it's behind the mirror in this case, and no light actually passes through it. So this is what we call a virtual image. So again, best way to think about a virtual image is if I put my pad of paper at that location at which the image is supposed to be created, no light would actually be passing through there. All the light is on this side of the mirror. So this is what we call virtual. So these are plane mirrors. So plane mirrors, they're about as boring as possible. So what happens is the image location is exactly equal to the object location, just with a negative sign. This negative sign means it's behind the mirror. So here, this negative just basically means it's behind the mirror. And the object height is exactly the same then as the image height. So good. So that brings us to our first group assignment of the day. Good. So our first group assignment, we're going to go, is here. So this says we have a student is standing between two plane mirrors, which are 6 meters apart. So this is total distance between the two plane mirrors. The student is standing 2 meters in front of the mirror on the right, as this thing says. And then it wants to know what is the position of the third image formed by the mirror. Okay. So we want to know that's what? If we stuck our head, for example, between two plane mirrors, what do we see? What we're going to see is an infinite number of copies of ourselves. That's what we're going to see. So basically, anytime you're at Walmart or any shopping place, especially if you're going to a place where, you know, they have all the deli meats and all that stuff that you can buy. So not the actual deli counter, but, you know, where they have the prepackaged meats. They usually have mirrors on the sides of those sections. So if you put your head in there and you look at yourself, what you'll see is there's actually an infinite number of copies of yourself going in both directions. So this is ultimately what you're going to see. So what will happen then is you're going to create an infinite number of you on this side. You're going to create an infinite number of you on this side. And what I want to know is where is the location of that third image that you see? So the third furthest one away from you. Okay. So basically what's going to happen is what? This mirror then is going to create an image of you here, which is 2 meters away from that. But this mirror here is going to create an image of you on this side, which is 4 meters away from the mirror itself, because you are 4 meters here. So now you're going to create one here. This one, which is now 2 meters away, is going to create also another image over here, because this is now going to be a total of what? So if this is 2 meters, this is another 2 meters. So this is 4 meters. So it's going to be a total distance of 8 meters away from this left mirror, which means then it's going to create another one over here, which is the third image. So basically all you're trying to do then is determine where is that location of that third image. And another fun question you can ask yourself is that third image facing you or is it facing away from you? So for example, if this person is looking this direction, so that this one is at the back of the head, are you going to see the back of your head or are you going to see you staring at yourself? That's what you want to know. Okay. So There are only, what, 4 of you, so I still will do a breakout room, but I'll only do one because there's only 4 of you, so I'll let all of you guys go in the same one. Should be fun. There we go. Okay. So discuss.
Years, and you could do all sorts of things.
Who knew that personal experience when you were a kid would come back now? I'm glad that I'm not the only one who did that.
Yeah.
Hello, ladies. I'm talking about sticking her head into things.
We were talking about like playing with the bathroom mirror, like the cabinet, like when you were a kid to create all those images.
Yeah, especially if you have one mirror on one side and one on the other side.
Principles of it, but pretty cool.
Very nice.
Right.
Yeah, see all that physics knowledge that you gained?
We observe physics every day. We just don't usually do the math.
That is true.
I'm still confused on like what I'm supposed to be like drawing.
Oh, so basically, you want to draw all of those multiple images. Okay, so let's kind of talk about it. Let me bring that up. So basically, yeah, so let's say here's the one mirror, here's the second mirror, and then here you are. Okay, my beautiful artwork. Great. So the first image you're going to create is the image from this guy here. Right? So basically what you know is that your first image you're going to create is this guy. So this is the first image. Okay? And what you know is if this is the distance 2 meters, then this distance also has to be 2 meters. Okay? Now, the second image you're going to create, which is a little bit further away, is now going to be this guy created here. Right? And again, what you know is if this is the distance of 4 meters, then this also has to be a distance of 4 meters. Now, this guy, though, is going to create an image from here because this is now a image. So this guy is going to create an image in this mirror. So basically what's going to happen then is this total distance from here to here now is going to be what? So if this is 4, this is also 4, so this is now 8 meters. This is now going to create another image out here where this is now going to be a total distance then of 8 meters. Okay. So what that means then is that what? This is the third image. So this is third. This is second. And this is first. So what that means then is that this image then is going to be what? A total distance of 12 meters away from you. So this total distance from here to here is now going to be 12 meters in front of you.
Okay.
Okay. Now let's make it a little more fun. So let's put in some hair. So if I put hair here, so on the back of the head, then this one is going to have hair here, which means that this one is going to have hair in the back here, where this one's going to have hair on this side. Okay. So basically the third image then, what you're going to be seeing is the back of your head. So this image, which is 12 meters in front, is then the back of your head. Is that okay?
Yes.
Good.
It's almost like you have to like map it out. You have to. My thing is
Yeah,
like,
you're trying to figure out which one is
the
creating
order.
what, right? So this second image, you're going to be looking at yourself, right? So your eyes are going to be over here. So you're looking at yourself. But this one, right, is coming from the fact that you're reflecting your back. So the back of your head is going to be what's facing towards you. And then since this one is creating the image over here, then it's just being reflected in the opposite direction. So yeah. So you're looking at the back of your head. So
Yeah.
back, front, front, back, back, front, front. That's it. This is also what we call parity. So parity means if you're looking in a mirror, what happens then is things switch sides. In a mirror, what happens is all your coordinates basically switch. So positive becomes negative basically on each side. So yeah. Don't worry too much about that. Should be good. Okay. So everyone doing okay? Not too bad. Nice easy one, right? Good. So good. So that is plane mirrors. You're all in breakout rooms still. Okay, let's stop sharing that. Get out of breakout rooms. Leave. Actually, let's close. All right. Great. So that's one type of mirror we can have to reflect and create an image from. But the second type is what's called a spherical mirror. So let's talk about spherical mirrors. So what's a spherical mirror? So a spherical mirror is exactly what you think of. So here, imagine that you started off with a sphere, which is a reflecting surface, and we're going to create two different types of mirrors from this by simply cutting it. So we're going to take and cut off a section here of the mirror. So basically, I'm going to remove this entire section. So here we're going to be able to create two different types of mirrors. So the first one is what's called a concave mirror, and the second one's called a convex mirror. So here's a concave. So the concave is when you're looking at that piece that you cut off, but the light is going to reflect off the inside portion. So this is what's called a concave mirror. And then a convex mirror is one where that section that you cut off, you're going to reflect then off of the outside portion of it. Okay. So what's the difference? So a concave mirror, what happens is if I send light rays parallel to this central line, which is called the principal axis, if I send in light coming in through the principal axis, what happens then is that these light rays are going to reflect, but they're going to reflect in the central part all coming through this single point here, which is called the focal point. So basically what happens is in a small region around the center here, in the spherical mirror, all these light rays are going to pass through this particular point, which is called the focal point. With the convex, what happens in that case then is if I send in light rays parallel again to this principal axis, the light rays are going to hit and then reflect outward, but all of these light rays appear to have come from this particular point, which is called the focal point. So these light rays are what's called diverging, so they're spreading out away from the mirror. But if I backtrack and I ray trace all of these lines backwards, all of these lines appear to have come from a single point, which is what's called the focal point. So here, the focal point is where all these light rays are being reflected into. So this is our concave. So here, if I look at concave. So here's my spherical mirror. This line here, which bisects the mirror, is what's called the principal. So this is the principal axis. So this is the bisecting line. Again, all these light rays at which I'm sending in, again, somewhere close to the center of this. Let's draw these guys. So these are all my incoming light rays parallel to the principal. Each one of these guys are going to reflect, so I'm going to use green for the reflecting, and they're all going to pass through a particular point, where that point then is what's called the focal point. Oops. There we go. That one. And finally, that one. So all these light rays are then bouncing off, going through, and they all pass through this particular point, which we're going to call F, where F is what's known as the focal point. So this is our concave. For the convex, oops, convex, there we go. In this case, again, what's happening is this spherical mirror is facing away from us. So now we're going to fire at the back side of it. So again, this is still the principal. This is still the bisecting line. But here the difference is all of these light rays of which I'm sending in. Let's draw a few of these. What happens then is these guys are going to hit and then reflect outward. But they're going to reflect outward as if all of them came from a central point. There. So it's going out that way. It's going to come this way. So these are then my reflected lines. All of these are seeming as if they came from this point, which again is simply called F, which is the focal point. Okay. Now, there's a caveat here, which you can actually see in that first figure. So if I look at light rays which are reflecting off of the mirror, which are very far away from kind of this small central grouping, what will happen is each one of these guys gets reflected, but they don't actually pass through the focal point. This is what's known as spherical aberration. So let's talk about spherical aberration. So spherical aberration is when light rays come in. So for example, let me draw these in blue. Oh no, I already used blue, so let's do yellow. So what happens in this case is these light rays are going to come in, they're going to reflect, but they're going to reflect in a location, that's not what I meant to do, not through the central point. So not through the focal point. So this guy's going to be reflected something like this, okay? So basically, this spherical aberration, what that does is anytime I'm dealing with a spherical mirror, these lines are going to miss the focal length or focal point, which is then going to cause the image to smear. So basically, it's kind of broaden the image and make it so you can't see the image very well. So this is actually a big problem in things like telescopes. So this is actually a huge problem for telescopes where you're trying to see something very far away, but the light rays which are coming in that aren't near this small area here, so this is some small focusing region, what they're going to do is they're going to smear what you would actually see the image. So if you're trying to see like a distant star or distant planets or something like that, that telescope then is going to cause it to become blurry, kind of become smeared due to these light rays which are coming in. And this happens for all spherical mirrors. The only way to get around this is to actually use what's called an elliptical mirror. So what happens in an elliptical mirror is it's actually not spherical, but it actually becomes more parabolic. So your spherical or elliptical mirror is something more like this, which is actually parabolic in shape. Parabolic / exponential in shape. Now, basically the reason for that is now because of the shape, these ones that are out here are actually still going to be reflected through the focal point. So you're not going to get the smearing, you're not going to get that kind of fattening out and blurring of the image. Now, the problem with elliptical mirrors, though, is that they're so much more expensive than spherical mirrors. So spherical mirrors are much easier to make and they're much cheaper to make as opposed to these elliptical mirrors. So basically, if you bought a type of telescope, it's called a reflecting telescope at, say, something like Walmart or, you know, what other stores exist? Oh, bought it on Amazon, something like that, something that wasn't too expensive, then they're typically going to be made from spherical mirrors. So the cheaper that the telescope is, then the more likely it's going to be some sort of spherical mirror. So these elliptical mirrors, they're really expensive. So these are things that, like the Hubble telescope, for example, and really expensive telescopes, that's what they're actually going to use. But this is different. So this is a concave. So again, a concave mirror is going to actually cause all of the rays to be passed through this point, which is called the focal point. For the convex, these guys are going to come in, bounce away. So these rays are now being diverged, but they're diverged in such a way that they appear to be resonating or starting at a particular point, which is called the focal point. So now we want to know is, how do we create images from these spherical mirrors? So we want to know now, what is the image formation from a spherical mirror? So let's draw a couple cases first. So for now, I'm going to concentrate on concave. So let's talk about concave and how we actually do that. So I'm going to warn you ahead of time, these are going to be some probably ugly drawings, but we're going to do our best. So here is our principle. Usually when I do this on the board in the classroom, I can at least bring in a meter stick and try to make it somewhat pretty, but yeah, it's not gonna work here. Okay. So first things first is we have the radius of curvature. So let's draw R. So R here, capital R, is equal to the radius of curvature. So the radius of curvature is the radius of the sphere. So this is equal to the radius of curvature, which is the radius of the spherical mirror. Next, we're going to define little f, where little f is what's known as the focal length. The focal length then is the distance from the back of the mirror here to the location of the focal point. So this is going to be our focal point f. And then little f, which is the focal length, is the distance from the back of the mirror to the location of the focal point. So this is distance from back of mirror to location of capital F, so to the focal point. So basically, what we're going to do is we're going to draw an object in 3 different locations. So we're going to look at 3 different cases. So let's do case number 1. So case number 1 is here we're going to draw our image at a distance of the our object. We're going to draw our object distance at a distance greater than that of the radius of curvature. So here I'm going to draw my object. So here's going to be my object. So we're going to represent our object by simply an arrow pointing upward. So this is my object. Okay. Now, to determine the location at which this thing is creating an image, we're going to draw typically 2 out of 3 principal rays. You don't have to draw all 3 principal rays. Typically 2 of them will be sufficient. So what are our principal rays? So ray number 1 is going to be the ray which goes from some point, which I'm usually going to draw from the tip of the object, which goes parallel to the principal. Okay, so this is our principal ray number 1. By the time it reaches the mirror, this thing again gets reflected through the focal point. So this is our principal ray number 1. Okay, so principal ray number 1 is the ray which goes parallel to the principal, hits the mirror, gets reflected through the focal point, and then goes off on its merry way in a straight line. Okay. Principal ray number 2, I'm going to draw that one in green. This one is going to go from the tip again. So I'm going to draw it from here. This one's going to go down through the focal point. Let's see if I can draw that. Good. Hit the mirror, and then once it hits the mirror, it's going to get reflected parallel to the principal. Okay, so this is ray number 2. Okay. So ray number 2 goes through the focal point, hits the mirror, gets reflected parallel to the principal. Ray number 3, I'm drawing yellow, is going to be the ray which goes and hits the back of the mirror directly at the principal line. So this one's going to come through here, hit directly at the principal. Okay, so this is number 3. Now, the law of reflections tells us that this angle here, theta, has to be the same as the angle at which it gets reflected at. Let's see if I can actually draw that. Good. And this guy is going to come out something like this. Okay, so that this angle here is the same as that angle. So this is number 3. Okay. The location where all 3 of these guys align themselves with is going to be the location of the image. So the image location here then is going to be this guy. So this is what we call our image. So the location where all 3 of those principal rays cross each other is then the location of the image. Okay. So here, notice that we can tell 2 things automatically, actually 3 things automatically about this location. So first thing we can see is that this is a real image. And it's a real image because, again, if I put a piece of paper here, all the light actually passes through it. Right? So here the light is coming in this direction, hits, reflects back off into this direction. So all the light is actually passing through this point. So this is a real image. The second thing we can see is that this thing is upside down. So this is what we call inverted. So this is what we call an inverted image. Inverted basically just means it's upside down. Okay. And the last thing we can see is that the location at which this thing is going to be created is somewhere between the focal point and the radius of curvature. So our image distance is going to be somewhere between the focal point and the radius of curvature. So when the object distance is greater than that of the radius of curvature, then the location of the image will be somewhere between the focal point and the radius of curvature. Okay. So this is case number 1. That was okay? So let's write down some things. So the distance from the location of the object to the back of the lens, or to, sorry, back of the mirror, this is what we call the object distance. So the object distance then is equal to the distance from object to back of the mirror. And then this distance here, I'll draw that one in blue. So this distance from the back of the mirror to the location of the image is what we call DI, which is the image location. So the image location then is going to be equal to the distance from back of mirror to the location of the image. Okay. So this is case number 1. Let's do it again. So now let's look at case number 2. So let's draw that one in red. So case 2. So for case number 2, again, here is my concave. So here's my concave. Okay. Make that all pretty. There we go. Here is my principal. There we go. Again, here's my radius of curvature. Here is my focal point. Okay. Good. So now let's put our object somewhere between the radius of curvature and the focal point. So this is going to be my object. So for this one, we have that the object distance then is going to be somewhere between the radius of curvature and the focal point. Okay. So now we want to know is where is the image location for this one and what type of image do we get? So to do this, do exactly those rays again. Now again, I'm only going to draw 2 of those. The first one I'm going to draw is ray number 1. So again, ray number 1 is going to go parallel to the principal, hit the mirror, and then get reflected through the focal point. So this is ray number 1. Ray number 2. What color did I use ray number 2 last time? Was that green? I think that was green. Yeah, I think that was green. Ray number 2 is going to go down through the focal point, hit the lens or hit the mirror, and then go parallel to the principal. So in this case, this guy's going to come down through here, hit somewhere here, and then get reflected back in this direction. So this is now ray number 2. Again, it's sufficient to do only 2 rays. You don't have to do all 3 rays. So these are the only 2 I'm going to do. So in this case, again, the location where these guys actually line up with each other or intersect is going to be the location of my image. So this is then my image. So this is my image. This is my object. Okay. So here what we can see is first observation. Again, this is a real image. Again, it's a real image because all the light rays are actually passing through this particular point. So if I put a piece of paper there, all the light would be concentrated there. So that would be a real image. Again, it is inverted. So this guy is upside down as opposed to the orientation at which he's supposed to be. And we can see is that what? The location at which this image is created is actually greater than the radius of curvature. So here the image location will be greater than the radius of curvature. Okay. So these are 3 observations we can make about this guy. Good, so that's case number 2. Case number 3, so let's do case number 3. I'll do that one in green. Let's see if I can draw it down here. Let's do case number 3. So case number 3 is now, again, we're gonna have our concave spherical mirror. So here's my concave spherical mirror. Here is my principal. There's my principal. Here's my radius of curvature. Here is my focal point. And in this case, we're going to put our object finally inside of the radius of curvature. Or sorry, inside of the focal point. So this is going to be my object distance. So here, my object distance then will be less than the focal point. Okay? So somewhere between 0 and that of the focal point. Again, we want to know what is the image location. So here, again, we're going to start off with ray number 1. Ray number 1, again, will be parallel to the principal. Hit the lens, or sorry, mirror, and then gets reflected through the focal point. So there is ray number 1. Ray number 2 in this case is kind of awkward to draw because the ray is supposed to go through the focal point initially, but the focal point is behind the actual object. So in this case, I'm actually going to draw ray 3 instead. So ray 3 is going to be the one that goes and hits the back of the mirror. And then this angle here has to be the same as this angle. So it's about the same angle. And then it's going to be reflected off in this direction. Okay. So this is now ray number 3. Okay. Everyone's okay? Now notice what's happening here though is ray number 1 and ray number 3 are actually diverging away from each other. So out in this region out here, the 2 rays are actually diverging. So what does that mean? So that means that ray number 1 is getting further away from ray number 3, which means these 2 lines are never going to cross each other, which means that the image formation cannot occur anywhere out here. So this is where we're going to have to use that idea again of ray tracing. So what's happening is our eye is out here. So this is the location of our eye. We're looking, these rays are going to come into our eye, but our eye is going to ray trace these lines backwards and try to figure out where these guys actually originated from. So this one I'm going to extend backwards along the same line that this is traveling. This one I'm also going to extend backwards along the line that this one is traveling. And let's extend our principal out into this direction. So what happens then is what? The image location that I see for my eye here, I'm going to ray trace backwards these lines, and I'm going to think that this image, or the parent object, came from behind the mirror where these two lines actually cross with each other. So where this one crosses with this one is actually going to be the location of the image. So this is actually my image. And this is going to be my object. Oops. Sorry. Do that in green. Good. So let's talk about this guy. So this guy is what's called, again, a virtual image. So this one gives us a virtual image because, again, if I put a piece of paper here, no light actually passes through this image. This is where I'm seeing it created, but it's actually on the back side of the mirror where no light is hitting because all the light initially goes this direction, reflects back in this direction. So there's never any light back here. So this is actually a virtual image. This is upright because it's in the same orientation at which the original object is. And we can actually see here that the image location is going to be what we call negative. Okay, so basically it's going to be on the back side of the mirror. So anything over here is technically a negative distance. Okay. So this is then the image formations for 3 different cases for my concave mirror. So when it comes to the concave mirror, case number 1, when this guy is greater than the radius of curvature. In this case, it's a real image, it's inverted, and the image distance is somewhere between the radius of curvature and that of the focal length. Case number 2, when the object is placed somewhere between the focal length and the radius of curvature, again, it's inverted, it is real, but the image location is going to be somewhere greater than that of the radius of curvature. In case 3, when it's inside of the radius of, inside of the focal length, this one is going to be virtual, upright, and it's going to be negative. So in this case, it's going to be on the back side of the mirror. Now, let's do one more, and let's look at the convex. So convex, there's only one case we can consider. So let's only talk about convex for one case. So this is my convex. Here is my principal. Here for the convex, again, our focal point is on the back side of the mirror. So this is my radius of curvature, this is my focal point, and we're going to put our object in front of the mirror, which means it's going to be somewhere out here. Okay. So this is going to be my object. Now this one is a little bit more tricky. So what's going to happen is ray number 1 is still going to be a little ray which goes parallel to the principal, hit the mirror, but unlike before where it gets reflected through the focal points, it's actually going to diverge away from the mirror along the line which connects to the focal point. So this is actually going to be ray number 1. So ray number 1 is going to go parallel to the principal, gets reflected and diverges away from the mirror as if it came from the focal point. Okay. So this is ray number 1. Ray number 2 then is the ray which is supposed to go through the focal point. So basically if I draw this guy going down in this direction, so if I extended him back here, he would actually go through the focal point. But since it actually is not going to go through the focal point, it's going to reflect. It's going to reflect then backwards, parallel then to the principal. Okay, so try drawing that a little bit better. Stop doing that. So that's let me draw my black line here, my green. So this one gets reflected backwards as if it's now going parallel to the principal. So this is ray number 2. Okay. Now again, this ray is diverging away from this ray. So what I want to do is trace this one backwards as if it came from the principal. And now this one, my eye, which is somewhere over here. So now this is the location of my eye. My eye is now going to ray trace this one backwards to see where this one appears to have originated from. So now I'm going to ray trace this one backwards. Okay. So the image location then is going to be the location where I ray trace this diverged line backwards through the focal point and ray trace this one, which is now parallel to the principal, backwards. So where these two guys cross, this is the location then of the image. So this is my image. Okay. So here we can see then that's what? This is a virtual image. This is upright. Upright, if I do a spell, there we go. And again, my image distance is negative. Okay. Because again, it's on the back side of the mirror. Good. So good. So let's talk about some of these things. So first of all, it turns out that for spherical mirrors, what happens is that the focal length is exactly equal to 1/2 of the radius of curvature. So this is always true for any focal or for any spherical mirror. So for any spherical mirror, what happens is that the focal length is equal to 1/2 of the radius of curvature. So if I know the radius of curvature, I know the focal length, it's simply 1/2 of that. Now, if I wanted to know the mathematical location of this image distance, so this is my image distance, we're going to use something which is known as the mirror equation. So what's the mirror equation? Mirror equation is basically derived from doing a whole bunch of geometry, which I'm not going to bother to do. I'm just going to tell you what it looks like, and we're going to talk about it from there. So the mirror equation says that 1 over the image distance plus 1 over the object distance is equal to 1 over the focal length. This is what's known as the mirror equation. Now, you have seen this before in lab. This is actually also what's known as the thin lens equation. So the mirror equation and the thin lens equation are actually identically the same. Okay. So how does this work? This works with a whole bunch of different sign conventions. So let's talk about the sign conventions. Good. Sign convention number 1. The focal length is positive for a concave mirror, negative for convex. So meaning that if it's on the left-hand side, as we drew here, of the mirror, so it's in front of the mirror, then this is going to be a positive focal length. Otherwise, it's negative. Okay. Number 2. Object distance is positive if it is on the same side that the light is coming from. Negative otherwise. So DO is negative otherwise. Now, every example we drew here, the object distance was positive. We always drew the object from the side at which the light was coming from. So in that case, every example we drew, it was positive. Okay. Sign convention number 3. The image distance is positive if it is on the same side that the light is going to. Negative otherwise. Okay. Okay? So that means that what? So let's go back to our pictures that we drew. So in case number 1, this would be a positive image distance because it's on the same side that the light is going to. So here, this is positive object distance because it's on the same side the light is coming from. So the light is moving, in this case, from left to right. So initially, it's moving from left to right. Once it reflects, it is now moving from right to left. So in this case, the light is going to the left. So this is on the same side at which the light is going to. So this is positive. This one is also positive because, again, the light is going from right to left after reflection. So this is on the same side as the light is going to. This one is negative because here the light is going initially from left to right, bounces, and then goes from right to left. But this is on the side at which no light actually passes through, so this is negative because it's on the opposite side. Is okay with this? Sign convention number 4. M, which is what's known as the magnification. So M is negative if inverted, positive if upright. Okay. M, which is the magnification, is either equal to the image height divided by the object height, or negative of the image distance divided by the object distance. So this is what's called the magnification. Now again, you've already seen this in lab, but that's this guy. So this is what we call the magnification. Good. So these are spherical mirrors. So again, spherical mirrors, we mostly draw them just to get an idea of what the image actually should look like. But in reality, we're just simply going to calculate them using the mirror equation as well as the magnification. So here, as long as we use these 4 different sign rules into this expression, we're never going to go wrong. So again, if we're using a concave mirror, this is going to be positive. If we're using convex, this is going to be negative. So we don't have any time to do any examples today, so tomorrow we'll do a bunch of examples of this to kind of see how all of this actually works together. Okay?
Could you go back to number 4 real quick?
Yes. So number 4 is the magnification is negative if it's inverted and positive if it is upright. Basically, the reason for that is because if I look here, right, if it is inverted, what happens is that the image distance is positive, the object distance is positive, so this becomes negative. But if it was upright, as we saw in those examples, the image distance is actually negative, so I get a negative, which makes that a positive, and this is pretty much always positive, so that's going to make this guy positive. So if it's upright, so typically the way this works is to be upright, it's going to be virtual, and to be inverted, it's going to be real. So if I'm dealing with just one mirror, typically what's going to happen is for it to be upright, this has to be virtual. And for this guy to be inverted, this is going to be real. Okay. So anytime I have a real image, it has to be inverted. And if I have a upright, it has to be virtual for one mirror. If I had more than one mirror, then that doesn't count anymore. So we'll talk about that later. Okay. Everybody's okay? So tomorrow we'll do some examples of this. We'll see how this guy actually works. And then we'll move on to lenses, which you've already did in lab, but we'll talk quickly about lenses, and then we'll talk about compounding all these guys on top of each other and how all that stuff works into real optical instruments, such as telescopes and microscopes and all that good stuff. Okay. So any other questions anybody might have before we kind of move on? Everybody's okay? So don't worry if you can't draw very well. As you see, my drawing is fantastic, so it should be okay. But again, the drawings are mostly there just to kind of get an idea of what these things should look like. So that way, when you mathematically solve them, you have an idea of, okay, did I do something wrong or not? Right? So if my picture shows that I should end up with a virtual image that's upright, and mathematically I find that it's a real image which is inverted, something went wrong somewhere. So it's a good way to try to figure out, okay, where did I go wrong? Was it in my drawing or was it in my math? So good. So like I said, we'll do some examples tomorrow, and then we will move on from there. So have a good night, ladies.